Greetings and welcome to lecture on exponential and logarithmic functions. Lecture 8.2, the inverse of a function. Greetings and welcome to the series of lectures on exponential and logarithmic functions. In this lecture, we'll discuss the inverse of a function. So what does it mean to be an inverse of a function? Well, if you think about a fraction, the inverse of a fraction, or the reciprocal of a fraction, is where the numerator and denominator switch places. Well, when we have a function, the x's and y's switch places. So we had a function f, and inside this function, we have points 1, 4, 2, 5, 3, 6, and 4, 7. The inverse of the function f is obtained by reversing the order of the coordinates. So the inverse of f will be 4, 1, 5, 2, 6, 3, and 4, 7. We reverse that order. Now it's not bad. When we're given the points, we just switch them. We reverse the order. But generally, we're not given a function in that sense. We're given a function as in something like y equals mx plus b. Well, how do you flip it? How do you know every single point and change the order of those points? So let's work through a problem and see how we're going to do it. So if a function f is defined as f of x equals 2x minus 3, we want to find the equation that represents the inverse of f. Well, remember, the inverse is where we switch the components. So the first thing we're going to do is interchange the components, and then the second thing we're going to do is we're going to solve for y in terms of x. Right, so here's our function, f of x equals 2x minus 3. And I'm going to go ahead and write that as y equals 2x minus 3. Our first step, let's interchange the components. And we'll rewrite it as x equals 2y minus 3. Right? So it's literally wherever the x was, I write the y. Wherever the y is, we write the x. That's the first step. Second step is we're going to take this x equals 2y minus 3 and we're going to solve for y. Add 3 to both sides. I get x plus 3 equals 2y. Divide by 2 on each side. Therefore, y equals x plus 3 all over 2. That is our inverse function of f. Let's take a look at these graphically. So our original function was y equals 2x minus 3. That's just a line. Negative 3 is the y-x intercept, and then I go over 1, up 2, over 1, up 2. And I can find a couple points, connect the dots, and bingo, I've got a line. Then I have y equals x plus 3 over 2. And I can set this up to where I can see slope and the intercept. Intercept is 3/2 and our slope is 1/2. So that's about 3/2. And I go over 2, up 1, over 2, up 1. As you see, the red line is where y equals x. And in essence, if I take that line and I flip over this line, right, if I flipped it, the blue line would become the green line, and the green line would become the blue line. They are mirror images using this y equals x line. Okay? Mirror images. They are, in essence, they have symmetry about y equals x because, well, if I have a point AB, then BA is always the symmetrical, always has symmetry around y equals x, right? Because we're just flipping. If I have 0, 1, I have 1, 0. Right? I'm always over that line. Let's try an example. Y equals x squared minus 2. And we want to also graph that function as well as its inverse. Well, y equals 2x squared minus 2 is a parabola. So let's keep that in mind. Inverse function we're going to exchange x's and y's, right? X equals y squared plus 2. And now we're going to solve it for y. Add 2 to both sides. Take the square root of y squared. I do have to say plus or minus. So my inverse function is y equals plus or minus the square root of x plus 2. Now how I'm going to graph these guys? For the first equation, my original function, I'm going to just plug in some values. 0, -1, +1, -2, +2, -3, +3, and I'm going to get its outcome, right? If I plug in 0, x to the 0 is 1, 1 minus 2 is negative. 0 squared is 0. I don't know why I said that. 0 squared is 0. -2 minus 2 is -2. Let's plug in 1. 1 squared is 1 minus 2 is -1. -1 squared is 1 minus 2 is also -1. So I just did it as a shortcut so I wouldn't have to do a whole bunch of values written out. And you'll see 2. 2 squared is 4. 4 minus 2 is 2. -2 squared is 4. 4 minus 2 is 2. And so on and so forth. For the inverse function, y equals plus or minus the square root of x plus 2, I want to be a little bit more careful about the values that I select. Let's plug in -2. -2 plus 2 is 0. The square root of 0 is 0. Let's try -1. -1 plus 2 is 1. Therefore, the square root of 1 is 1. So I get plus or minus 1. 2. 2 plus 2 is 4. The square root of 4 is 2, so it's plus or minus 2. And then I'm going to select 7, because 7 plus 2 is 9, and the square root of 9 is 3, so it's plus or minus 3. When I graph these, here's what I get. The green function was our original function, y equals x squared minus 2. And the blue function was its inverse of y equals plus or minus the square root of x plus 2. Again, you'll see that along this x equals, or the y equals x line, you'll see that the points mirror each other. There's symmetry. I had -2, 0, and therefore I'm going to have 0, -2. They're symmetrical. Just keep in mind, sometimes the inverse is not a function. Remember, to be a function, you have to pass the vertical line test. Looking at the green and only the green, I hit 1 point, 1 point, 1 point, 1 point, 1 point, 1 point, all the way through that whole entire function. Looking at the blue, I hit 1 point, but as soon as I get off of that, I hit 2 points, 2 points, 2 points, 2 points. Therefore, the blue function, the blue equation is not a function. The inverse is not a function. But that doesn't mean that the inverse will never be a function. In fact, if the function is a one-to-one function, meaning for every x element there is only one y element, then it is a one-to-one function. And therefore, not only the original function is a function, but the inverse is a function as well. For example, if my function is 2, 3, 1, 3, 5, 8, it is not a one-to-one function because the 3 on the second element repeats. But if I have another function, g, 5, 7, 3, -1, 4, 2, none of the components repeat. Therefore, it's a one-to-one function. And therefore, the original function is a function as well as its inverse will be a function. Now that's great, we could do all of that, but if we're looking at a graph and we want to know if it is a function, we have the vertical line test, right? If it only hits 1 point in our graph, then it is a function. Well, if we want to know if its inverse is a function, we look at a horizontal line test. And if we only hit one point on the horizontal line test, then we know that the original function's inverse will be a function and that it's actually a one-to-one function. So for example, let me get back our graph here. Our green is our original function. Vertical line test, it passes. But horizontal line test, it doesn't, and therefore we know its inverse will not be a function. We do have some special notation for inverse function. If y equals f of x, if it is a one-to-one function, then we can state that the inverse function is also a function because it's one-to-one. It's going to pass the vertical as well as the horizontal line tests. And therefore y equals f of -1 of x. That -1 means its inverse. Just like if I had 2 to the -1 power, that would make it 1/2. The numerator and denominator switch positions. Well, this is saying switch components of the x and y, that -1. All right, so let's try and find the inverse of a one-to-one function. So let's try g of -1. First thing I want to do here is I'm going to rewrite this in terms of x's and y's. So y equals x minus 4 over x minus 2. Okay, that's our original function. Now we need to interchange our x's and our y's. X equals y minus 4 over y minus 2. Now that that step's done, we need to solve for y. But it's not that easy because I have y's in a couple different locations here. So here's my plan. I'm going to multiply both sides by y minus 2. Okay. That way, at least the denominator is gone on the right-hand side, giving me x times y minus 2 equals y minus 4. Okay, my goal is to get y's all on one side. But this y is attached to a -2. So I'm going to go ahead and distribute the x. X times y minus 2x equals y minus 4. Now I can get rid of this 2x by saying plus 2x. That doesn't have a y in it, so I'm going to move that to the right-hand side. So I have xy equals y plus 2x minus 4. Again, my goal is to get y's all onto one side. So I'm going to go ahead and subtract a y on the right, subtract it on the left. I'm left with xy minus y equals 2x minus 4. Right there. We're almost there. I can't get rid of this x yet, but I can factor a y. I can factor this left-hand side, so I have y times x minus 1 equals 2x minus 4. Okay, I can factor it out. Now, if I divide the left-hand side by x minus 1, do that same thing on the right, I will get a function that says y equals 2x minus 4 all over x minus 1. Only y is on the left, so therefore the inverse function is 2x minus 4 over x minus 1. Little tricky. Got to kind of plan out your strategy. Trying to figure out what you need to isolate is the hard part with solving these equations. So let's look at the graphs of our original function g of x equals x minus 4 over x minus 2 and our inverse function of 2x minus 4 over x minus 1. Looking at our original equation, x cannot be 2. If x is 2, then we're going to run into a problem, right? If x equals 2, then we get a 0 in the denominator. So we have a vertical asymptote, right? A vertical asymptote of 2 when x equals 2. Now, how do we get this horizontal asymptote? Well, y cannot be 1 because if we exchange the positions of x and y, remember this y cannot be 1 because 1 minus 1 is 0 in our inverse. So there is a horizontal asymptote here, right? So x will not be 1 here, but y does not want to be 1 here either. So there's an asymptote here. All right, so then when we plot these guys, we're just going to select a few points, like 0, 1. Right? If we put a 0 in, 0 here, we're going to get a 2. 0, 2, 1, 2. Right? If we put in a 1, negative 1 over negative 3 is 3. And we keep going, we can plot the first point. Knowing that it's mirrored, right, I could use this vertical asymptote and the horizontal asymptote as my new, we can think of it as, pardon me, our new origin. Like where they cross is our new origin, and then we have that xy that goes through it, and we can mirror that. Right? I know it's a little bit tricky to see or tricky to use in the beginning, but if we just shifted everything back to the original origin, you'll see that it aligns perfectly with the xy line. Otherwise, just give yourself some x values, find the y value. X value, y value. You'll see the exponential function, the inverse of the exponential function, or inverse of the function show up. Sorry, I'm tongue-tied right now. Dun, 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 dun. No, it's not what I want. No. Let's take another quick look at another function. All right, so y equals 2x. We've already seen this function before, but then we want to look at x equals 2y. X equals 2y. We're just going to use the y equals x line to be able to mirror the points. So the first thing I want to plot is y equals 2x. So plug in a 0, you get 1. Plug in a 1, you get a 2. Plug in a 2, you get a 4. And if you plug in a negative 1, you get a half. So you get these points. 1/2, 1/4, 1/8, 1, 2, 2, 4, 3, 8. Right? Now I'm going to use this line to mirror the points. Well, if I'm 0, 1, I must be 1, 0 here. If I'm negative 1, 1/2, I'm 1/2, negative 1. So 1/2, negative 1. If this point is, and I can also see that it's mirroring across the line, right? Otherwise I can think of it as 1, 3 or 3, 1. And then I have 4, 2 and 8, 3. 8, 3. But you do see that they're mirrored across this line, right? If the line went right here, I'm one diagonal box away, one diagonal box away. The line crosses, I'm within that same box, but I'm at the corner, right? At the corner here. So you could use that line to plot the graph. I think it's easier just to switch the components myself. The last thing I want to talk about in this lecture is functions, relationships, and inverse, just a summary of these guys. So a relation is just like having coordinates x and y. Right? So here are some facts. Every function is a relation, but not every relation is a function. Remember, we have to pass the vertical line test for it to be a function. Every function has an inverse, but not every inverse is a function itself. It has to pass the horizontal line test. If it does, if the original function, meaning it already passed the vertical test line, the vertical line test, if that function passes also the horizontal line test, then its inverse is going to be a function. The domain of a function is the range of the inverse. The range of the inverse, the domain of the function is the range of its inverse, and the range of the function is the domain of its inverse. That just means x's and y's switch positions. If y equals f of x, if it's a one-to-one function, we can represent that as f of -1 of x to represent the inverse. The graph has symmetry around x equals y. And then, just to be very clear, if AB belongs to the function, then BA belongs to its inverse. So that's it. Happy holidays, and be seeing you.